If we launched a starship today, how long would it really take to cross just one light year? Years, centuries or so long that no one who leaves would ever see the end. You hear people say that star is 4 light years away, and your brain quietly files that under very far in time, not very far in distance, alright? So let's strip the confusion out. Light year means distance, nothing else. It is simply how far light travels in 1 year. Light is fast. In a vacuum, it covers about 300,000 kilometers every second. That is around 186,000 miles every second. Now take that speed and keep it going for 1 full year, about 31.5 million seconds. When you multiply that out, you get a distance of about 9.46 trillion kilometers, roughly 5.88 trillion miles. That number is what 1 light year really is, a fixed, enormous length on the cosmic ruler. So when you ask how long would it take us to travel 1 light year, you're not asking how long is a year, you're asking how long does it take to cross 9.46 trillion kilometers, starting from the kind of speeds humans can actually reach. As soon as you frame it that way, you can test your intuition against real numbers and see how badly it breaks. Start with something you understand, how fast you move on your own feet. A typical walking speed is about 5 kilometers per hour, around 3 miles per hour. Now, keep that speed without stopping, no sleep, no food breaks, just constant motion. At that rate, crossing 1 light year would take on the order of 216 billion years. The age of the universe is about 13.8 billion years, so we're talking more than 15 times that span, just to cover a single light year at walking speed. Walking is clearly useless here, so upgrade to something that feels fast, a commercial jet. A big passenger plane cruises at about 900 kilometers per hour, around 560 miles per hour. You cross an ocean in under a day, you move between continents in hours, but keep that jet pointed in a straight line toward a target 1 light year away. Keep it flying without refueling and you are still looking at more than 1 million years of travel time. Human civilization has only been around in anything like its current form for maybe 10,000 years. Your fast plane needs around 100 times that span to cover a single light year. At this point, you can already see the pattern. The numbers are not slightly uncomfortable, they're ridiculous. Everyday speeds, even the fastest ones you experience, collapse when you hold them up against 9.46 trillion kilometers. A light year is not just far, it is far enough that cars, jets, even most spacecraft might as well be standing still on the galactic scale. To get some grip on that, shrink the problem down to a structure you already know, our own solar system. The average distance from Earth to the Sun is about 150 million kilometers, and astronomers use that as a basic unit called 1 astronomical unit, or 1 AU. It is a yardstick for talking about orbits inside our system. Now compare that to a light year. 1 light year is about 63,000 astronomical units, so if the Earth-Sun distance is 1 step, a light year is 63,000 of those steps in a row. Take the orbit of Pluto as a practical example. At its farthest, Pluto is roughly 49 astronomical units from the Sun. That sounds huge. It is beyond the classical planets, but 49 compared to 63,000 is tiny. In light year units, that maximum Pluto distance is less than 0.001 light years. Not even 1/10 of 1%. Even the paths of our most distant spacecraft are still only a few hundred astronomical units out, a fraction of a light year. Every physical journey humans have ever launched sits inside a bubble that does not even reach 1,000th of the distance of a single light year. That is the first hard reality you have to accept. Our entire travel history is confined to a very small neighborhood. So the moment you start talking seriously about traveling 1 light year, you are stepping out of the solar system comfort zone into a regime where even our best examples look like baby steps. Now connect that to something else you have heard, the distance to the nearest star beyond our own sun. The closest star system to us is Proxima Centauri, and its distance is about 4.24 light years. That number is not decoration in a textbook, it is the real distance to the nearest potential destination outside our system. So when you ask how long would it take to travel 1 light year, you're really asking, do we have any hope of getting even a quarter of the way to the nearest star in a time that makes sense for human beings? Because if 1 light year already takes thousands of years with our best technology, then 4 and a bit light years is not a mission, it is a multi-civilization project. This is where the question stops being abstract and becomes practical. You know that light can cross a light year in 1 year, by definition. You know that your current machines, the ones you ride in and the ones you launch, are nowhere close to that. The key problem is not defining the unit, it is closing the gap between how far light goes in a year and how far your hardware can go before everyone involved is dead and forgotten. So the real mission here is not to memorize that a light year is 9.46 trillion kilometers. The real mission is to ask, with actual engines, obeying the real laws of physics, built from materials we can at least imagine, how close can you realistically push a spacecraft toward the speed of light? And once you choose a speed, whether it is a slow crawl or a serious fraction of light speed, what does that do to the travel time for a single light year? Does it give you a time scale you can plan around like decades? Or does it spit out numbers so huge that the whole idea turns into science fiction again? And here is the uncomfortable part. You are going to see that falling short of light speed does not just cost you a bit of time, it punishes you. Even at a tiny slice of light speed, like 10%, that 1 light year still takes around 10 years from the point of view of an outside observer. Drop your speed to what we can do now and those same 9.46 trillion kilometers stretch into thousands of years. The distance is fixed, the punishment for being slow is not. So with that scale burned into your mind, the next step is simple and a little painful. If you take the fastest machines humans have already launched, no future tech, no untested ideas, and you ask, how long would those actually take to go 1 light year? What answer do you get? And how far away does that put us from ever treating a light year as a normal trip? Right now, with the hardware you actually have, the question is simple and a little brutal. If you take the fastest machines humans have already built and thrown into space, how long do they need to cross 1 light year? Start with the champions, not average rockets, the record breakers. Probes like Parker Solar Probe have been pushed to extreme speeds using rockets plus gravity assists, stealing a bit of momentum from planets and from diving deep into the sun's gravity well. When you look at numbers like that, you see velocities in the range of about 60 to 70 kilometers per second relative to the sun. In everyday units, that is roughly 216,000 to 252,000 kilometers per hour, about 134,000 to 157,000 miles per hour. That is not fast for a plane, that is fast enough to circle Earth in a few minutes fast. These are not sci-fi ships, these are real objects already flying out there. So if this is what your best tech can do right now, boosted by clever gravity tricks and decades of rocket engineering, what happens when you point that speed at a full light year and ask for a straight shot across 9.46 trillion kilometers? Time is distance divided by speed, so take that 9.46 trillion kilometers and divide it by 70 kilometers per second, the upper end of those probe speeds. You get a travel time of about 135 billion seconds. When you convert that into years, by dividing by the number of seconds in a year, you land on something around 4,300 years for 1 light year. That is with generous assumptions using the higher speed, and pretending you can instantly accelerate to that speed and hold it perfectly the whole way. Think about what 4,300 years means in human terms. Written history from the first real cities and records in places like ancient Mesopotamia is only a bit older than that. If you launched a probe at that speed when the earliest civilizations were rising, it would still not have finished 1 light year today. Your summer vacation distance in space, at your current best speed, already spans the entire history of writing, cities, empires, and everything you would call human civilization. If that sounds a bit abstract, connect it to another speed you already use in space, the orbital speed of your own planet. Earth's orbit moves around the Sun at about 30 kilometers per second, which is roughly 108,000 kilometers per hour, about 67,000 miles per hour. That is already faster than most of your probes relative to Earth, and it's completely driven by gravity, no fuel burned. Now, say you somehow upgrade your technology so that your Starship can cruise at twice that speed, 60 kilometers per second, using some future high-end chemical or electric system. Even with that upgrade, you're still in the same ballpark as those 60 to 70 km per second probes, so your trip time to 1 light year is still in the thousands of years. At those speeds, before you reach the 1 light year mark, you would complete over 4,000 full orbits of the Sun. In other words, you could spin around your star thousands of times, year after year, and only then would your ship have crossed a single light year in a straight line. That gives you a hard feel for the mismatch between planetary speeds and interstellar distances. So the obvious question is, if we already have rockets and they work, why not just build a bigger one, strap on more fuel, add more engines, and push the speed higher until 1 light year comes down into a reasonable range? Here is where the physics starts shutting doors. All of those speeds we just talked about, from launchers to deep space probes, come from chemical rockets. They all rely on the energy stored in chemical bonds, things like liquid hydrogen and liquid oxygen burning together, or kerosene and oxygen. Chemical energy has a fixed limit, a certain amount of energy per kilogram of fuel, and that directly caps how fast your rocket exhaust can go. That exhaust speed then limits how much you can increase the velocity of the rocket itself without making almost all of the rocket into fuel. The core rocket math, usually called the rocket equation, says that to get a bigger change in speed, you either need a higher exhaust velocity or you need a higher ratio of total rocket mass to final dry mass, which basically means more of your rocket is fuel, less is payload and structure. With chemical fuel, the exhaust speed is only a few kilometers per second, something like 3 to 4.5 kilometers per second. That's fine for launching off a planet and moving around a solar system, but to reach even a small fraction of light speed, like 1% of light speed, you would need insane mass ratios, where almost everything is propellant, and your actual ship is tiny. So chemical rockets hit a hard ceiling for interstellar missions. No matter how you stack stages, or what clever configuration you pick, once you push into fraction of light speed territory, the fuel requirements explode. That is why, at our current level of technology, using only chemical propulsion, a 1 light year trip is effectively a multi-millennium journey, not something you can compress into a single human lifetime. Now, look at the scale of the problem more directly. With today's best probe speeds, you're looking at over 4,000 years to go 1 light year. If you want a mission that arrives in 50 years instead, you need to cut that time by a factor of about 80 or more. If you want 10 years, you need to cut it by over 400. Since time for a fixed distance goes down as speed goes up, that means you need to increase your speed by at least 1 to 2 orders of magnitude, so by factors of 10 to 100 compared to those 60 to 70 km per second probes. And here is the nasty twist. Energy does not just scale linearly with speed, it goes roughly with the square of the speed. So if you want to go 10 times faster, you need about 100 times more energy per kilogram. If you want to go 100 times faster, you're talking about 10,000 times more energy per kilogram. That is not a small engineering upgrade. That is a completely different class of propulsion, and a completely different energy economy backing it. So you are not missing the target by a little bit. You are off by orders of magnitude. To make 1 light year doable within a single human life, you're forced to jump from speeds that take millennia to speeds that take decades or less, and the physics bill for that jump is enormous. At this point, the honest question becomes, what exactly is in this rocket equation that makes speed so expensive, and what kinds of propulsion could even start to close this gap? Here's the part that really hurts. You already know rockets work, so why can't you just build a bigger one, pump in more fuel, and push your way to light year speeds? The answer is, there's a piece of math baked into every rocket that quietly ruins that plan, and it's called the rocket equation. In normal words, the rocket equation says this: the amount your ship can change its speed, its total delta V, torr, depends on 2 things: how fast you throw exhaust out the back, and how much of your starting mass is fuel versus actual ship. The change in speed is basically exhaust speed times a logarithm of the mass ratio, where that mass ratio is your starting mass divided by your final empty mass. If you want a higher final speed, you either need exhaust that blasts out much faster, or you need a rocket that starts out mostly fuel and ends up almost empty. There is no third option. Chemical rockets, the kind we actually build now, hit exhaust speeds of about 3 to 4.5 kilometers per second, which is roughly 2 to 3 miles per second. That might sound huge, but in space terms, it's not. With numbers like that, your total possible change in speed stays in a depressing range unless you turn the vehicle into almost nothing but propellant. That's why real launch vehicles are skinny tanks with a tiny payload stuck on top, not big roomy starships. The math is forcing that shape. So the obvious follow-up is, okay, how much delta V do you really need if you're serious about crossing 1 light year in something like a human timescale, not thousands of years? If you want a 1 light year trip to fit inside a few decades from the point of view of people watching from home, you're talking about cruise speeds around 10% of light speed. 10% of light speed is about 30,000 kilometers per second, or roughly 18,600 miles per second. Now compare that target speed to a chemical rocket's exhaust speed of about 4 kilometers per second. Your desired change in speed is around 7,500 times your exhaust speed. When you feed a factor that big into the rocket equation, the logarithm turns that into a required mass ratio that is insanely large, so large that you can just call it impossible for engineering. You're in the territory where the amount of fuel you would need is not just more than your payload, it is more than any sensible structure could support. You're asking chemistry to do a job that its energy density simply cannot handle. So in plain language, chemical rockets are not just inconvenient for 10% of light speed travel, they are physically incapable of getting you there with any realistic ship. That pushes you to the next question. If chemistry is too weak, what if you upgrade the exhaust speed with better physics? Do things improve enough to matter? There are more advanced ideas on the table. Nuclear thermal rockets use a reactor to heat hydrogen and throw it out the back, and those can, on paper, get exhaust speeds of maybe 8 to 10 kilometers per second, around twice what chemical rockets manage. Electric propulsion like ion engines can do even better in terms of exhaust speed, pushing into the 30 to 50 kilometers per second range, which is roughly 10 to 15 times higher than typical chemical exhaust. That sounds impressive, and it is for mission inside a solar system, but even 50 kilometers per second is only about 0.00017 times the speed of light. To reach 10% of light speed with that exhaust speed, your total change in speed has to be about 600 times your exhaust speed. Plugging that into the same rocket math still gives you an enormous mass ratio. You're still in the nightmare zone where the rocket is almost all propellant, and the actual ship is a rounding error. So yes, these advanced engines help a lot for Mars or the outer planets, but for crossing 1 light year in decades, they are still stuck inside the same basic trap. Now here's where the trade-offs get brutal in a very practical way. Every time you demand more total change in speed, the required fuel mass does not go up in a straight line, it grows exponentially. That means a small jump in desired final speed can make your fuel mass explode. But an interstellar ship is not just a fuel tank with a seat strapped on. If you want to send humans, you need real structure, you need radiation shielding, you need life support, food, water, air recycling. You might need spinning habitats to give you something close to 1G, so bones and muscles do not fall apart over years. Even for a robotic probe, you still need computers, communication systems, power systems, and some protection from radiation and micrometeorites. As the rocket equation pushes you to pack on more fuel, that fuel mass itself makes everything harder. More fuel means a bigger structure to hold it. More structure means more mass. More mass means you need even more fuel just to move it, and the spiral gets worse. You get forced into a corner where your choice is basically build a ship that is ridiculously huge and mostly propellant, or accept a lower speed that makes 1 light year take hundreds or thousands of years instead of decades. So your normal intuition, shaped by cars and planes, tells you, if I want to go faster, I just add a bigger engine and a bigger tank, no big deal. The rocket equation looks at that and says, you can try, but the cost in mass and energy is going to explode on you. The universe is charging a very high tax on velocity, and you pay it through that mass ratio. That is why when you look at a light year with honest physics, it stops being just a long drive, and turns into a regime where classical rocketry basically fails as a tool. You can still play around inside a solar system, you can still do heroic missions to nearby planets, and maybe icy moons, but the moment you start asking for 1 light year in decades instead of millennia, you are crossing a line. You're already talking about propulsion that pushes far past current rockets, far past basic nuclear thermal, into concepts that turn entire atoms into energy, or that avoid carrying fuel at all. So the next hard question is, if regular rockets cannot do it, and even upgraded exhaust speeds still choke on that distance, what happens when you go to the next level and start using nuclear reactions themselves as your engine? Can turning atomic energy into thrust finally crack this speed barrier for a single light year? So if normal rockets are trapped by the rocket equation, the next step is blunt, you stop burning molecules, and you start using atoms themselves for thrust. The question is, does that finally make 1 light year feel like a mission? Or is it still absurdly far even when you bring nuclear fire into the engine? Start with the cleaner, more controlled option, nuclear thermal rockets. Instead of burning fuel and oxidizer, you run a fission reactor. You pump liquid hydrogen through the reactor core, heat it to extreme temperatures, and throw that hot hydrogen out the back. The physics here is straightforward. Hotter exhaust means faster exhaust. Faster exhaust means more delta V for the same mass ratio. In lab tests and serious design studies, you see that nuclear thermal concepts can roughly double or even triple the exhaust speed compared to chemical rockets. So instead of 3 to 4.5 kilometers per second for the exhaust, you might get 8 to 10 kilometers per second, maybe a bit more, which is around 5 to 6 miles per second. That alone is a big deal inside the solar system. With that kind of performance, trips that currently take months, like Earth to Mars, could drop to a few weeks depending on the exact trajectory. You burn less time coasting on slow orbits and more time actively steering. For missions to the outer planets, you claw back years. So for local exploration, nuclear thermal is a serious upgrade. It sits in that near-term box of things humanity could realistically build and test. But if you turn that same idea toward a light year, the scale problem hits you again. Let's push the optimism. Say you combine nuclear thermal propulsion with clever staging, maybe multiple burns, plus gravity assists where you can, and you somehow get your Starship up to a sustained cruise speed of about 200 kilometers per second. That's 720,000 kilometers per hour, around 447,000 miles per hour, which is very fast by any current standard. Now hold that speed against the actual distance. 1 light year is 9.46 trillion kilometers. Divide that by 200 kilometers per second and you get something like 15 billion seconds of travel. Turn that into years and you're sitting at roughly 475 years for 1 light year. That is a huge improvement at over the 4,000 plus years you got from current probe speeds, but it is still far beyond 1 human lifetime. You've basically moved from "this is older than history" to "this spans multiple human generations," more like a moving colony than a single mission with 1 crew. So nuclear thermal rockets bend the curve, but they do not break it. They tell you, yes, you can go faster than chemistry, but they do not give you the factor of 10 or 100 in speed that you really want if you're trying to hit 1 light year in a few decades. That leads to the more aggressive nuclear idea, nuclear pulse propulsion. Instead of a steady reactor heating hydrogen, you fire actual nuclear bombs behind the ship. The rough layout is, you have a huge shock absorber system and a massive pusher plate at the back. You eject a nuclear explosive, it detonates some distance behind you, the blast slams into the pusher plate, the shock absorbers smooth the kick, and the ship gets a shove forward. Repeat this thousands of times. The reason people ever took this seriously is because each small nuclear device carries far more energy per kilogram than chemical fuel. If you can convert even a fraction of that into directed thrust, you effectively get exhaust speeds in the tens of kilometers per second or higher, and by stacking many pulses, you can push the ship into the thousands of kilometers per second range. Some studies have shown that, on paper, if you accept very harsh engineering trade-offs, you might accelerate a large ship up to something like 3,000 kilometers per second. 3,000 kilometers per second is about 1% of the speed of light, so roughly 0.01 c. In imperial units, that's around 1,860 miles per second. Now take that speed and run it against the same 9.46 trillion kilometre distance. At 0.01 c, ignoring acceleration and deceleration phases for a moment, crossing 1 light year takes on the order of 100 years. Suddenly the travel time drops out of the thousands of years regime and lands in the 1 century regime. That changes the tone of the answer. 100 years is still longer than a normal human lifespan, but it is not longer than a civilization's memory. You could launch such a mission, record why you did it, maintain the project, and have the arrival still matter to the descendants of the people who started it. It moves from mythic timescales into something closer to a long national or global project. But before you get too comfortable, you have to look at what you are actually signing up for with Nuclear Pulse. First, you need to handle thousands of nuclear detonations in sequence, each timed precisely, each interacting with your pusher plate and shock absorbers without tearing the ship apart. The mechanical stresses are extreme, the material fatigue is serious, and the failure modes are catastrophic. Lose control of the timing or the distance of the blast and you are not slightly off, you are in pieces. Second, you are dealing with enormous radiation and activation problems. The pusher plate and surrounding structures take repeated nuclear blasts. They heat, they erode, they get bombarded with high-energy particles. Keeping that hardware intact over the whole acceleration phase is not a small engineering problem. You would need advanced materials, advanced cooling, and a very deep understanding of how those repeated shocks degrade your structure over time. Third, the legal environment is hostile to the idea. There are treaties that specifically restrict nuclear explosions in space and the use of nuclear weapons outside tests. Building a system that intentionally detonates thousands of nuclear devices would run straight into international law, public fear, and massive pushback. Even if the physics is fine and the engineering is barely within reach. So yes, nuclear pulse propulsion can, on paper, pull your 1 light-year travel time down to something like a century at around 1% of light speed, but you get that only by accepting a propulsion architecture that is extreme in every sense, technical, social, and legal. And yet, this is the first point in the whole discussion where the situation stops feeling like a joke. Nuclear concepts show that speeds around 0.01 c are not forbidden by physics. They look ugly, hard, and dangerous, but not impossible. At 1% of light speed, 1 light year in roughly 100 years becomes a real number you can write down without laughing. That is still beyond a single person's lifespan, but it sits inside the range of a long-running project for a technological civilization. So the picture shifts. With chemistry, 1 light year is thousands of years away. With nuclear thermal, you might cut that to a few centuries. With nuclear pulse, you push it toward a single century. The wall is cracking, but it is not gone. To get that 1 light year trip down into a span that fits cleanly inside one lifetime, maybe 10 to 20 years, you need even more extreme performance. You need energy densities far beyond fission bombs, and you need exhaust speeds that start to look like a serious fraction of light speed itself. So the next step up is obvious. If splitting heavy atoms and detonating bombs can only get you to about 1% of light speed, what happens if you switch to fusing light atoms instead? Can fusion engines finally push your 1 light year travel time into the single-digit decades? Here's the blunt question now. If splitting atoms with nuclear pulse drives can barely drag 1 light year down to around 100 years, what happens when you jump to the next level and start fusing atoms instead? Can that finally push a light year into a time frame that feels like a serious project instead of a legend? The reason people keep calling fusion the holy grail of propulsion is simple: energy density. Chemical fuel gives you a certain amount of energy per kilogram. Nuclear fission gives you many orders of magnitude more. Fusion, turning light nuclei like hydrogen into helium, gives you roughly 1,000,000 times more energy per kilogram than chemical fuel. With that kind of energy, you can, in principle, throw exhaust out the back of your ship at thousands to tens of thousands of kilometers per second. That is not a small upgrade, that is jumping from a bicycle to a jet fighter in one step. One popular picture in fusion propulsion is the pellet-driven engine. You store tiny capsules of fusion fuel on board. Each capsule may be milligrams or grams. You feed them into a reaction chamber many times per second. Each capsule gets blasted by powerful lasers or particle beams. It compresses, heats up to fusion conditions, explodes into ultra-hot plasma, and that plasma is magnetically directed out the back as thrust. Think of it more like a machine gun of controlled micro-explosions than a steady flame. Because each tiny burst is so energetic, the exhaust can, in concept, reach speeds of several thousand kilometers per second, maybe even into the tens of thousands. That exhaust speed is the key. The higher it is, the more total change in speed you can get from a reasonable amount of fuel, and the more you escape the nightmare mass ratios of chemical rockets. Fusion is attractive not because the word sounds cool, but because the numbers finally match the scale of a light year. So if you plug that level of performance into the 1 light year problem, what do you actually get? Does it move the needle enough to matter? Old studies like the famous Project Daedalus design did that back-of-the-envelope work. They assumed a large unmanned probe using fusion pellets, with a multi-year acceleration phase, then a long cruise, then maybe a deceleration phase at the end. The target cruise speeds in those concepts were around 10 to 20% of light speed. 10% of light speed is about 30,000 kilometers per second. 20% is about 60,000 kilometers per second. In miles, that's roughly 18,600 to 37,000 miles per second. Now, look at those speeds against a single light year. At 10% of the speed of light, ignoring the time you spend speeding up and slowing down, you cross 1 light year in about 10 years as measured by someone watching from your starting point. At 20% of light speed, you drop that time to around 5 years. This is the first time in this entire discussion that you get a single-digit years answer for a light year without cheating and without using fantasy physics. That difference is huge. We just walked from thousands of years at probe speeds to hundreds of years with nuclear thermal or nuclear pulse fission, down to 5 to 10 years with optimistic fusion drives. You're still talking about very aggressive engineering, but the travel time number itself finally looks like something you could put on a mission schedule instead of a myth list. So why aren't we building these already? If the math is this attractive, what is holding fusion back? Here's the reality check. Right now on Earth, we do not have a single commercial fusion power plant that produces net energy. We can cause fusion in devices like tokamaks and laser-driven experiments, but we spend more energy driving the confinement and heating systems than we get back as useful output. Holding a plasma at hundreds of millions of degrees, keeping it stable, and extracting energy is already extremely hard in a giant, heavy, stationary machine bolted to the ground. Now push that one level up in difficulty. A fusion rocket needs to do similar things in a device as a whole. It has to be compact, lightweight enough to launch or build in space, resistant to intense vibrations and thermal cycles, and reliable over years or decades with no maintenance yard nearby. It also has to channel a good fraction of its fusion energy into directed exhaust, not random radiation that just cooks the ship. That is not just a harder version of the same problem, that is multiple extra layers of engineering hell. And yet the important point remains. Nothing in known physics says you cannot do this. There is no law that forbids a fusion rocket. The barrier is technological, not fundamental. We do not yet have the materials, the control systems, or the long-lived reactors to build a Daedalus-style engine in real life, but the equations themselves do not block it. So if fusion is that hard, why does it still matter so much for the 1 light year question? What does it buy you beyond just raw speed? The key gain is in exhaust velocity and what that does to fuel fractions. If your fusion engine can push exhaust out at, say, 10,000 kilometers per second, which is about 1/3 of light speed, you suddenly get access to large changes in ship speed without needing a rocket that is almost all propellant. The change in speed to exhaust speed ratio is no longer thousands. It can drop to numbers that give sane mass ratios. In plain words, with fusion, you can design a starship where a reasonable fraction of the total mass is actual ship, not just fuel. You have room in the budget for thick shielding against radiation and dust, for serious life support systems, for big water tanks, for structural redundancy, for communication gear, and for scientific payload. You also have enough delta V to not only accelerate up to a high cruise speed, but to slow down again at the other end, instead of just doing a high-speed flyby. This is a fundamental shift compared to chemical or even basic nuclear thermal designs. Those systems trap you in a corner where, if you chase high speeds, you end up with a vehicle that is 99.999% propellant and almost zero payload. Fusion pushes you toward ships that are still big and heavy but not absurd. The basic architecture moves from barely a shell around a fuel tank to an actual starship with systems and safety margins. So, when you combine all of this, what does it do to your answer for 1 light year, not just as a raw number, but as something that fits into a human life? If you can reach a cruise speed of about 10% of light speed with a fusion drive, then even after you account for the years spent accelerating up and braking down, 1 light year in roughly 10 to 15 years starts to look feasible in principle. You launch, you spend a few years ramping up speed, you cruise, you decelerate, and the total mission time still fits inside the time frame of a long career. That means you could, in theory, launch a mission when you are young, work on it through midlife, and see data coming back from a destination 1 light year away before you die. For an unmanned probe, that is completely acceptable. For a crewed mission, it would still be extremely demanding, but it would no longer be automatically ruled out by biology and time. This is the moment where the question how long to travel 1 light year finally gets an answer like about as long as training for flying and retiring from a very long, very intense job, instead of longer than your species has had agriculture. Fusion does not magically solve all problems, but it compresses the map. The nearest stars stop being permanently later and become difficult but schedulable. But even if fusion fixes the propellant problem, there is another way to attack the rocket equation entirely by not carrying your fuel at all. So the next pressure point is obvious if you leave the heavy power source at home and push ships with beams of light or microwaves instead. Can you make that 1 light year trip even shorter? And what new problems does that introduce? Here's the next move that really bends the rules you're used to. Instead of fighting the rocket equation by cramming more fuel onto the ship, you sidestep it by not hauling the main energy source at all. You leave the heavy power system at home and you push the spacecraft with light itself. The core idea is called a beamed sail. You build a very lightweight, highly reflective sail, maybe made from advanced nano-layered materials, spread over a large area. The spacecraft, the actual payload, is tiny compared to that sail. Back home, in orbit around Earth, or on the surface of the planet or the moon, you build a huge array of lasers or microwave transmitters. Those beams hit the sail, reflect, and transfer momentum. Because the craft carries almost no propellant, its mass is low, and because the energy comes from fixed infrastructure back home, you're no longer limited by how much fuel you can lift off a launch pad. As long as you keep the beam on, you keep accelerating, and in principle you can push that sail up to a significant fraction of the speed of light, c. Now put some numbers on that. Concept studies that take this seriously do not talk about giant crewed starships first. They go after very small probes, gram to kilogram scale. Think of something the size of a chip or a small CubeSat. With masses that low and sail areas that are big compared to the payload, the push from the laser can be strong enough to drive the probe to speeds around 20 to 30% of light speed, roughly 0.2 c to 0.3 c. That means 60,000 to 90,000 kilometers per second, which is about 37,000 to 56,000 miles per second. Run that against 1 light year again. At 0.2 c, the probe needs about 5 years in the rest frame to cross 1 light year of distance. At 0.3 c, that drops to just over 3 years. Suddenly, 1 light year away stops meaning farther than the age of civilization, and drops into the same kind of timescale as the time between your birth and your younger sibling's birth, or the time between major generations in a family. The distance itself did not change, but by removing the propellant and shrinking the payload, the travel time collapsed by orders of magnitude. So that sounds great. So far it feels almost too good. And that means there is a bill hiding somewhere. The cost is not small. It shows up in the power and the infrastructure you need to make this work. To push even a tiny craft to 0.2 C or 0.3 C in a reasonable acceleration period, your laser or microwave array has to dump enormous power into the sail continuously and keep it focused over huge distances. We are not talking about a few megawatts. You're in the range of gigawatts to terawatts of power. For comparison, a large nuclear power plant outputs on the order of 1 gigawatt. A terawatt is 1,000 of those. So you're talking about energy usage comparable to a big fraction of current human civilization, focused into a tight beam. On top of the raw power, you have to keep that beam aimed at a sail that could be millions of kilometers away, correcting for tiny deviations, keeping the spot where you want it, and doing all of this while the sail is constantly accelerating and moving out of your neighborhood. The beam has to be phased precisely if it's made of many individual emitters, so the light adds up in the right direction and does not just spread out uselessly. The engineering here is at the scale of planetary infrastructure. You do not just build a big laser, you build a phased array the size of a city or larger, feed it with an entire energy grid, and control it with extremely precise optics and software. And then there is the sail itself. The sail needs to be very light, extremely reflective and thermally stable. It has to sit in a beam with very high intensity without melting, tearing or warping to the point where it spins out of control. It has to remain stable under constant acceleration, potentially many thousands of times weaker than 1G, but applied over months or years. If it wrinkles, folds or starts tumbling, the probe loses control. So the material science and control systems for that sail are their own major challenge. You need something that is closer to a precision optical element than a simple sheet. Even if you solve the acceleration side, there is a second major problem waiting at the far end of the trip, stopping. Pushing something away from home with a laser is conceptually straightforward. You keep shining until you reach your target speed. But when the probe is 1 light year away, your home laser cannot easily be turned around to slow it down. The geometry is wrong. The push is always away from you. If there is no matching laser or microwave array at the destination, the probe is basically on a one-way ballistic trajectory. It will scream through the target region at 0.2 C or 0.3 C, grab whatever data it can in a very short time window, and then head off into deeper space, never to return. For a 1 light year trip, depending on your acceleration profile, you might spend years forcing the probe up to cruise speed and then blast right past your target in hours or days. You get a fast flyby, not a slow, detailed survey or an orbit. To slow down without destination infrastructure, people have proposed tricks. One is to use the sail itself as part of a braking system, for example, turning it into a magnetic or electric scoop that interacts with the thin interstellar medium, using that tiny drag to bleed off speed over long distances. Another is to reflect a second beam from the home system off interstellar dust, or a reflector to push back on the sail. But that quickly gets complicated and inefficient. In all cases, deceleration remains one of the hardest pieces if you want the probe to arrive and stay, not just flash through. So beamed sails absolutely crush the outbound rocket equation for small probes, but they do not make the overall problem trivial. They shift the burden from the spacecraft to the civilization that launches it. Instead of building a giant rocket, you build a giant laser array and a giant power grid to feed it. The cost moves from one big vehicle to an entire system. If you can pay that price, the payoff is huge. 1 light year is no longer a distance you shrug off as basically unreachable. It becomes a mission timeline measured in years, not ages. You can send multiple small probes to different targets, separated by only a few years. You can build a program where every decade new missions launch, cross a light year or more, and send back data, building up a network of tiny sensors in nearby space. You stop being limited to watching stars and planets from afar with telescopes, and start poking them directly with hardware. At that point, the local region of the Milky Way turns from a static sky map into something more like a lab, You can test how real planetary systems behave up close. You can sample dust and gas in the interstellar medium. You can map magnetic fields and radiation environments directly. The time to cross a light year drops into a range where scientists can propose a mission, build it, launch it, and still be alive to analyze the results. But this creates a new kind of pressure too. If you know you can cross a light year in 3 to 5 years with small probes, it raises a more uncomfortable question. How do you protect those probes and maybe, later, crewed ships from everything they will hit at those speeds? And how do you deal with the fact that even with beams and sails, the universe is still pushing back with dust, gas, and raw kinetic energy as you try to go faster? You've seen that pushing speed up is brutally hard, but there's another twist hiding in the background. Once you get close to light speed, even your idea of how long a trip takes stops behaving the way you're used to. At low speeds, the world is basically Newton's world. Distances are fixed, clocks tick the same everywhere, and if you go faster, the time to cross a distance just scales in a simple way. That picture is fine for cars, planes, even normal rockets. But once you get to around 10% of light speed, about 0.1 c, Newton's rules are only an approximation. Push harder to half the speed of light, 0.5 c or 80%, 0.8 c or 90%, 0.9 c, and those old rules actually give you the wrong answers. Relativity takes over. The key effect here is time dilation. In plain language, the faster you move relative to some outside observer, the slower your onboard clock runs compared to theirs. Not because the clock is broken, but because that is how space-time behaves. At walking speeds or jet speeds, the difference is so tiny you never notice it. At 0.5 c or 0.9 c, the difference is big enough to add up over years. So the basic question changes. When you talk about how long a light-year trip takes, whose clock are you talking about? Take a concrete example. Say you somehow manage to get your starship up to 0.9 c, 90% of the speed of light. That is about 270,000 kilometers per second, roughly 167,000 miles per second. From the point of view of someone watching from Earth, if the ship could instantly be at that speed and hold it, crossing 1 light year of distance would take a bit more than 1 year, around 1.11 years. That's just distance divided by speed. 1 light year divided by 0.9 times light speed gives you that number. But that is only half the story. On the ship, you experience less time than that because of time dilation. Relativity says there is a factor that tells you how much your clock slows down at a given fraction of light speed. At 0.9 c, that factor is about 2.29. That means that, compared to the outside world, your onboard time is compressed by that amount when you are at cruise. So while Earth sees a little over a year go by during that 1 light year segment, the people on the ship feel only roughly half a year passing during the same segment of the journey, ignoring acceleration and braking. Stretch that out to longer distances, and it gets even more dramatic. Think about a 10 light-year trip at 0.9 c. From Earth's perspective, ignoring the speed up and slow down phases, it takes a bit over 11 years to go 10 light-years one way. Add a similar time to come back, and a simple round trip is over 20 years of outside time before you correct for more realistic acceleration. Once you include those acceleration and deceleration phases, you end up in the ballpark of 20 to 30 years for observers at home. On board, because of that factor of about 2.29, the crew sees something very different. Those same 10 light years of cruise compress into about 5 years of ship time each way, plus extra for the acceleration legs. So a round trip that costs 20 or 30 years on Earth might feel more like 10 to 15 years to the people on the vessel. In other words, the ship's crew and the people at home do not agree on how long the mission lasted. Even for exactly 1 light year, once you account for realistic ramps up to 0.9 c and back down again, you can end up with a situation where Earth measures a little over a year plus the acceleration time, while the ship logs noticeably less than that. The difference is not massive at 1 light year, but it is real. And as you stack more distance, the gap keeps growing. So now the simple question, how long does it take to travel 1 light year, split into 2 different questions. One is, how long does it take according to clocks on Earth, or in the rest frame of the galaxy, the frame where you measure distances like 4 light-years to Proxima Centauri. The other is, how long does it take according to the people actually riding the ship in their own proper time? At relativistic speeds, these two numbers are not the same, and there is no single universal answer everyone agrees on. This breaks your everyday intuition completely. You're used to time being absolute in normal life. If a flight takes 8 hours, everyone agrees it took 8 hours, whether they were on board or not. Near light speed, that rule fails. The universe not only charges you a huge energy bill to go fast, it also gives you a strange benefit. Your own subjective time can shrink compared to the outside world. From your point of view on the ship, long trips across many light years can be squeezed into a human lifetime, while people back home see decades or even centuries tick by. There is a cost though, and it is not just energy. The faster you go, the more out of sync you become with the place you left. If you go on a mission that takes, say, 12 years for you on the ship but 30 or 40 years on Earth, you return to a world that has moved on by an extra generation. Your own clock says one thing, your home planet's clock say another. So using relativity to compress your travel time always comes with the social and emotional price of leaving your original timeline behind. This is the real shift in thinking. Once you bring relativity into the picture, you realize that you can, in principle, trade energy for subjective time. If you pour enough energy into acceleration and push your cruise speed close enough to light speed, you can cross not just one light year, but many, in what feels to you like a handful of years. From the outside frame, your trip always takes at least distance divided by speed, and it can never beat 1 year per light year as seen from that frame. But from your frame, the one on the ship, the journey can be much shorter. So now, when you ask how long is a light year trip, you have to be precise about what you mean. Do you mean as measured by observers staying behind in the galaxy's frame, watching your trajectory, or as measured by the crew living through the journey on board? At low speeds, it doesn't matter, the answers match. At high, relativistic speeds, those answers diverge, and the gap is exactly the thing that makes near light speed travel tempting for long distances and deeply disruptive for any connection to home. And all of that is before you deal with a nastier question. Even if relativity lets you squeeze your own travel time, can the ship itself physically survive ploughing through the thin gas and dust between the stars at those speeds? Or does the interstellar medium turn into a deadly sandblaster the closer you push toward light? You've seen how hard it is just to get fast. Now here's the part most people ignore. The universe does not just sit there and let you blast through it. It hits back. The space between stars sounds empty, but it is not a perfect vacuum. On average, you've got roughly 1 particle per cubic centimetre. A mix of atoms, ions, and tiny dust grains, plus a few larger bits scattered around. At the speeds you're used to, cars, planes, even current spacecraft, that density is effectively nothing. You glide through it and never notice. But once you start talking about 0.1c, 0.2c, 0.9c, that nothing becomes a constant stream of high-energy projectiles. Think about a dust grain, something weighing micrograms, way smaller than a grain of sand. At airplane speeds, it's harmless. At 10% of light speed, that same piece of dust slams into your hull like a tiny bullet. At 50% of light speed, it gets worse again. By the time you're near 90% of light speed, it stops being useful to compare it to normal bullets at all. You're into hyper-relativistic impact territory, where even small masses hit with absurd energy. The reason is simple physics, and it's nasty. The kinetic energy of something in motion scales with half the mass times the velocity squared. The important part is the velocity squared, not the mass. If you double the speed, you don't just double the energy, you quadruple it. If you multiply the speed by 10, the energy goes up by a factor of 100. Now look at the jump we've been talking about in this whole Lightyear story. Take a fast current probe doing about 70 kilometers per second and compare it to 0.1c, around 30,000 kilometers per second. That is a speed increase of roughly 430 times. Square that factor, and the energy of an impact goes up by almost 200,000 times. So a bit of dust that would barely scratch a slow-moving spacecraft suddenly hits like a serious weapon at 0.1 C, pushed towards 0.5 C or 0.9 C, and the energy per impact explodes even further. So if you want to send a ship or even a fragile instrument across 1 light year at a significant fraction of light speed, you can't just worry about getting up to speed. You have to ask, how do you survive trillions of kilometers of this invisible hailstorm? The straightforward answer is you add shielding. You put a thick layer of material on the front of the ship, you accept that the leading edge is going to get chewed up, and you design it to absorb or vaporize incoming particles before they hit anything critical. Maybe you use dense materials, maybe you use layered structures, maybe you put a big sacrificial bumper out in front. But shielding is heavy. Every extra centimetre of armour costs you mass. More mass means more energy needed to accelerate. More energy means bigger engines, more fuel, or more power from your laser arrays. That pushes mission costs up, and in many designs, it also stretches the time you spend accelerating and decelerating. So the faster you want to go in order to shrink your 1 light year travel time, the more you are forced to pile on shielding, and that, ironically, pushes you back toward the slower trips, because your craft gets heavier and harder to push. This is not just a design annoyance, it's a feedback loop. You say, I want 0.2 C instead of 0.1 C, so you raise your speed target, which raises impact energies by a factor of 4. To survive that, you beef up your shielding. That makes the ship more massive. To get that heavier ship to the new higher speed in the same amount of time, you need more power or more fuel, which adds even more mass, and the spiral continues. At some point the math stops closing, and you either accept a lower speed, or you design a ship so extreme that it becomes almost impossible to build. Because of that, people look at alternative protection strategies. One idea is to use magnetic fields to create a kind of bow wave in front of the ship, especially to deflect charged particles. You generate a strong magnetic field. It pushes charged particles aside before they reach the hull, so fewer of them hit your physical material. Another idea is to deliberately carry a thin, sacrificial layer out front, maybe a cloud of gas or dust released from the ship, so incoming particles hit that first, vaporize, and turn into a hot plasma that spreads out, reducing the concentrated damage on the main structure. You can also imagine using a plasma shield, where the ship continuously ejects material forward, ionizes it, and shapes it with magnetic fields into a kind of glowing, protective bow shock. That way you are constantly replenishing the material that takes the hits. All of these ideas push the worst impacts into a region where you can afford to lose material without losing the ship. But again, the same problem appears. The faster you go, the more brutal each impact becomes, and the more intense the energy dump into your shield or bow wave. For a 1 light year run at 0.1 C, you have to survive not just one hit, but an enormous number of hits, spread over trillions of kilometers. Your protective systems have to hold up the whole way, not just for a few minutes. That means wear, erosion, heating, and long-term damage all become part of the budget. So your timeline for a 1 light year journey is no longer limited only by how much Relativity your engine can deliver. It is also limited by how much punishment your shielding can take before it fails. You can, in theory, design a ship that can handle 0.5 C, but maybe it can only survive a certain amount of distance before the front layers are ground away. That, in turn, sets an upper bound on how fast you dare to go for a given journey length. This is the invisible sandstorm problem. The light year is not an empty runway where you can just stamp on the throttle and go as fast as your engine allows. It's full of tiny bits of matter that become more and more dangerous the faster you try to cross it. There is a serious physics-driven limit on how short you can make that travel time before you are simply shredding your spacecraft faster than you can protect it. So your question quietly changes. It's no longer just how long does it take to travel 1 light year if I can reach some speed. It becomes how long can I afford to take given the engines I have, the energy I can pay, and the fact that the universe itself starts trying to kill my ship once I push too close to light speed. And that leads to the next hard constraint. Even if you solve propulsion and shielding, you still face one more brutal bill: the raw energy you have to pour into the ship just to get it moving that fast across a single light year. The numbers there are not gentle either. You've seen how speed, dust, and shielding all fight you, but there's a deeper limit underneath all of that. How much raw energy you can afford to throw into a single ship just to make it cross 1 light year fast. Start with a concrete ship, not a fantasy dreadnought. Say your fully loaded starship, including structure, shielding, crew, life support engines, everything, comes out to 1,000 tons. In scientific units, that's 1,000,000 kilograms. Now give that ship a serious cruise speed, 10% of light speed, about 0.1 c. In meters per second, that's roughly 30 million. In kilometers per second, about 30,000. In miles per second, roughly 18,600. The kinetic energy that corresponds to is given by half the mass times the square of the speed. So you take that 1,000,000 kilograms, you multiply by half, and then you multiply by the speed times itself, 30 million meters per second times 30 million meters per second. When you run those numbers, you land at something like 4.5 times 10 to the power of 20 joules. That is the energy just to spin this ship up to 0.1 c one time, ignoring losses, ignoring heating, ignoring that you also need to slow it down again at the end if you want to stop at your destination instead of just blasting through it. So what does 4.5 times 10 to the 20 joules actually mean in human terms? Is that small, big, or insane? Right now, the whole of human civilization, all the power plants on Earth combined, all the oil, gas, coal, nuclear, hydro, wind, and solar we use in a year, add up to an energy use on the order of 6 times 10 to the 20 joules. That's the rough scale of 1 year of global energy consumption. So to accelerate that 1,000-ton ship to 0.1 c, you are spending about 3/4 of everything humanity currently uses in a year. If you also want to decelerate it at the destination, you can roughly double that total. Now your one mission wants more than a full year of total global energy output just for the speed change, and that is for 10% of light speed. If you decide you want to push harder, to 0.2 c or 0.3 c, the energy bill doesn't scale in a gentle way. Because kinetic energy depends on the square of the speed, doubling the speed multiplies the energy by 4, tripling the speed multiplies it by 9, so going from 0.1 c to 0.2 c multiplies your energy requirement by 4, from roughly 4.5 times 10 to the 20 joules up, into the range of almost 2 times 10 to the 21 joules. Pushing to 0.3 c multiplies the original by 9, putting you well into the mid-10 to the 21 joules range. Very quickly, you are not talking about a big project, you're talking about multi-year, civilization-scale energy budgets compressed into a single mission. That immediately raises the question, where do you even get that energy from? What kind of fuel or power system can you use without carrying an impossible amount of mass? Chemical fuels, the stuff you burn in current rockets, give you on the order of 10 million joules per kilogram, 10 to the 7 joules. That sounds large until you put it next to what you need. If you tried to power a 10 to the 21 joule mission with chemistry alone, you'd need on the order of 10 to the 14 kilograms of fuel, 100 trillion kilograms, just in raw energy terms, before any losses, before any inefficiencies, and before you account for the rocket equation. That's obviously not happening. Nuclear fission, splitting heavy elements like uranium, jumps you up dramatically into roughly 10 to the 14 joules per kilogram. Fusion, turning light atoms like hydrogen into helium, can, in principle, reach around 10 to the 15 or 10 to the 16 joules per kilogram. Once you are asking for 10 to the 20 or 10 to the 21 joules for a single mission, you're pushed straight into that nuclear and fusion territory. No other known energy source has the right order of magnitude. That is why when people talk seriously about interstellar speeds and 1 light-year trips in decades, they almost always end up with nuclear drives or beamed power systems. The energy scale basically forces it. But having a powerful energy source is only part of the story. You also have to deal with the waste heat. No real system is perfectly efficient. Engines that convert stored energy into thrust will leak some fraction as random heat into the ship and its surroundings. Power systems that feed lasers or drive fusion reactions will also produce waste heat. And in space, you cannot dump that heat into air or water, you can only radiate it away as infrared light. That means you need radiators, large surfaces that run hot enough to glow in thermal radiation and carry away heat. Suppose your total mission life cycle involves dumping something like 10 to the 16 or 10 to the 17 joules of waste heat. To get rid of that without cooking your own ship, you need radiator surfaces sized and engineered carefully, with materials that can run at high temperatures without failing, and with geometry that lets them radiate efficiently without blocking your own engines or instruments. If your radiators are too small or your systems run too hot, the internal temperature of the ship creeps up. Electronics degrade, structures weaken. Humans, if they are on board, cannot survive. So you have to either build enormous radiators, which add mass and complexity, or accept lower operating power and lower acceleration, which lengthens the time you spend speeding up or slowing down. Once again, trying to rush the trip and make your 1 light-year time as short as possible pulls in big engineering penalties somewhere else in the design. So when you put all of this together, the picture is clear. Crossing 1 light-year quickly is not just a question of which engine you bolt to the back of the ship. It is a full-scale energy problem. You're effectively packaging the annual energy output of an advanced planet, maybe several years' worth, into one vehicle and its supporting infrastructure, and then expecting that system to run reliably for a decade or more in deep space. That changes the meaning of the original question. When you ask how long would it take us to travel 1 light-year, you're also asking, how much of our total energy economy are we willing to dedicate to one mission, one ship, one experiment? Because if you want the answer to be 10 years instead of 10,000 years, the cost is not just technical, it is civilizational. You're committing global-scale resources to push one machine across 9.46 trillion kilometers. And even if you solve that energy bill, there's still one more layer. You then have to ask whether human bodies, human biology, and human societies can actually survive and stay functional over those travel times under radiation, altered gravity, and closed life support. So the next pressure point is obvious. Even if your engines and energy budget say yes, does your biology say no to a 1 light-year run in human time? You've seen that engines, energy, and shielding are brutal, but there's another hard limit that doesn't care about equations at all, your body. Interstellar space is not just dark, it's full of high-energy particles, cosmic rays, and bursts of radiation from distant events. Even at low speeds, if you sit out there for years to decades, those particles will slowly drill through you and your ship. On Earth, you're protected by the atmosphere and magnetic field. In deep space, you're not. Over a mission of 10, 20, 50 years, the dose adds up. Radiation is measured in sieverts. A few sieverts delivered quickly can be fatal. A fraction of a sievert per year over long periods can greatly increase cancer risk. A 50-year journey at moderately high speed out in interstellar space could easily expose an unshielded crew to tens to hundreds of sieverts. That is thousands of times higher than typical yearly background exposure on Earth. Without heavy shielding, you're not talking about slightly higher cancer risk. You're talking about guaranteed damage, cancers, nervous system issues, maybe acute radiation sickness during strong events. To avoid that, you need thick shielding around the living areas, maybe several tens of centimeters of water, plastic or other hydrogen-rich material, or meters of regolith if you use something like asteroid rock. You might arrange water tanks and fuel around the habitat to soak up part of the radiation. That shielding mass adds up fast, and every ton of shielding is a ton you have to push to 0.1 C or more. So biology doesn't just say, add shielding. It reaches back into the propulsion and energy problem and makes them harder again. Radiation is only one side. Gravity, or the lack of it, hits you too. We already know from months-long stays on the International Space Station what microgravity does to people. Bone density drops, muscles atrophy, heart and blood vessels adapt in ways that are bad for long-term health, fluids shift toward the head, eyesight can change, astronauts can exercise hard every day and still come back with measurable damage after half a year. Stretch that from 6 months to 10 years, and the problem stops being hard but manageable and becomes you might not be able to stand, walk, or function when you arrive. So for a light-year mission on human timescales, you almost certainly need artificial gravity. That means either spin habitats like big rotating rings or cylinders that create centrifugal force, or long ships that accelerate at some fraction of 1g in a straight line for a long time, then flip and decelerate using the thrust as gravity. Both options are heavy. A spinning habitat needs strong structure, bearings, radiation shielding, internal floors, life support hardware, and safe connections to non-spinning parts of the ship. A continuous thrust ship that keeps you near 1g for months demands engines and power systems that can sustain that thrust, which ties straight back into massive energy and fuel requirements. Either way, giving your bones and muscles something like Earth gravity makes the ship more complex and more massive. Again, biology pushes the engineering up a notch. Then there's simple life support math. A typical human needs a few kilograms of water and food per day. Even if you recycle water aggressively, you still need some buffer. Over a decade, one person might consume many tons of resources if you treated everything as one way. Scale that to a crew of, say, 20, and you're talking about hundreds of tons of supplies if you don't recycle. Over 50 years, it gets completely out of hand, so you don't have a choice. You need closed-loop systems, oxygen recycling, CO2 removal, water purification, and some way to grow food on board. You're basically building a small, fully artificial ecosystem. Short tests like sealed habitats and space station experiments show that keeping such closed systems stable, even for a few people over year-scale durations, is hard. Gases drift out of balance, nutrients cycle in unexpected ways, microbes evolve, plants behave differently in microgravity or artificial lighting. Scaling that to decades in a moving starship turns life support from a complicated machine into a constantly monitored and adjusted environment, more like running a small planet than running a plane. Now look at time again, but from a biological and social angle. If your 1 light-year trip takes 100 years, there is no crew in the usual sense. The people who leave will not be alive at arrival. You're talking about a generation ship. Children are born on the way, grow up in the ship, have children of their own, and those later generations are the ones who actually reach the destination. The ship is not just a vehicle, it's an entire society, with education, culture, and conflict, all happening in a closed metal world between the stars. If your trip is 50 years, it is still borderline. You could, in theory, launch crew in their 20s and have them arrive in their 70s, but that assumes perfect healthcare and very low missions stress. If your trip is 10 to 20 years, now a single group of people can realistically start and finish the mission within one lifetime. They train, launch, travel, work at the destination, and either settle there or return data. The difference between 10 years, 50 years, and 200 years for 1 light year is not a small detail. It completely changes what kind of human group you are designing for, a crew or a multi-generation civilization in a can. So even if the physics department tells you yes, with fusion and beamed power you could do 1 light year in 5 years of outside time, biology might still push back. Radiation might be too intense unless you accept huge shielding mass. Long periods in altered gravity might still damage bodies unless you build complex artificial gravity systems. Your closed ecosystem might be too fragile to trust for decades without resupply. And on top of that, the psychological load of living in a confined space with a small group with no way out for years or decades is its own limit. That's why when you ask how long would it take us to travel 1 light year, the answer is not just a single physics number like 10 years at 0.1 c. The real answer sits at the intersection of propulsion, shielding, life support, medicine, and sociology. It's not only how fast can you push the metal, that's how long can you keep a tiny, fragile human world alive, healthy and sane in deep space before something breaks. And that leads straight into the next hard split. If human bodies and human psychology make long light year missions so demanding, Does it even make sense to send people first? Or does it make far more sense to let robots take the brutal high-speed, high-radiation missions, while humans stay home and wait for the data? Here's the hard contrast now. If you stop trying to keep humans alive on the ship, the whole 1 light-year problem changes shape completely. The moment you drop the requirement for air, water, food, gravity, thick radiation shielding, and soft tissue, your starship can shrink from a 1,000-ton habitat down to a 1-kilogram probe, or even less. The physics of kinetic energy is simple. It scales linearly with mass and with the square of speed. So if you keep the target speed the same, say 0.2 c, 20% of light speed, and you cut the mass by a factor of 1,000,000, from 1,000,000 kilograms down to 1 kilogram, the energy you need drops by that same factor of 1,000,000. Back when we talked about a 1,000-ton ship at 0.1 c, you saw that you were in year of global energy use territory. Now picture the same engines, the same giant laser array, the same power infrastructure, pushing a 1-kilogram payload instead. The power that would barely budge a giant crewed ship can fling an entire cloud of tiny robotic probes to 0.2 c and beyond. You stop thinking in terms of one starship and start thinking in terms of a spray of chip-sized vehicles, all crossing a light year in just a few years. Radiation, which was a near showstopper for humans, is much easier to deal with for electronics. You can harden chips against radiation, design circuits that tolerate bit flips and resets, and shield the most sensitive parts with a few millimeters or centimeters of material. You don't need meters of water or rock around a human body. A level of radiation that would kill a human crew in a few years might just shorten the lifetime of a probe's electronics a bit, or cause rare glitches that software can detect and correct. That means you can afford to push robotic probes to higher speeds before the shielding mass becomes a serious problem. For a robot, 0.2 c to 0.3 c, 20 to 30% of light speed, is far more realistic than for a crewed craft. At 0.2 c as before, 1 light year takes about 5 years in the outside frame. At 0.3 c, you're down to a little over 3 years. With robots, you can talk about those numbers without having to design rotating habitats, huge water tanks, medical facilities, and all the other systems humans demand. There's a catch though. Even if your probe crosses a light year in 5 years, information still cannot travel faster than light. Signals from your probe come back at the speed of light c, not at the probe's speed. So when that probe is 1 light year away, any radio or laser message it sends home takes 1 year to arrive. If you send a command from Earth, that takes 1 year to reach the probe, and another year for its reply to get back. The absolute fastest possible back and forth conversation with something 1 light year away has a 2-year round-trip delay, no matter how fast the probe itself is moving. That means travel time and communication time obey different rules. You might get a probe to its target region in 3 to 5 years, but you will still wait a year for its first high-resolution images or measurements to reach you. If you want to adjust its behavior based on what it sees, you are always issuing commands based on data that is at least a year old. So robotic missions at these distances have to be highly autonomous. You're not flying them in real time, you're giving high-level goals and letting them decide details on the spot. Robotic payloads have one more massive advantage: redundancy. With humans, you don't casually launch 1,000 crews and see which ones make it. With gram-scale or kilogram-scale probes you can. A beamed sail system or high-power fusion drive can, in principle, launch hundreds or thousands of tiny probes in a campaign. Some will fail on launch, some will be hit and destroyed by dust or debris, some will malfunction on the way. But you only need a fraction of them to survive and arrive to get useful data. This changes how you frame the 1 light year problem. Instead of asking, how do I build one giant craft that can stay alive for decades and arrive intact, you ask, how many small, cheap, hardened probes do I need to launch so that, statistically, enough of them survive a short, violent sprint to the target? You trade reliability of a single vehicle for reliability of the swarm. The risk is spread out. The loss of a few units is expected, not catastrophic. Put all of that together, and the conclusion is pretty direct. The first time your species crosses a light year in under a decade in any practical sense, it will almost certainly be with robots, not people. The numbers are just too strong. A 1 kilogram probe at 0.2 C is energy affordable once you have the right power and beaming infrastructure. A 1,000-ton crewed ship at the same speed is not, at least not with anything like current or near-term capabilities. For humans, interstellar travel on light-year scales is a problem measured in decades to centuries of technological and social development. For robots, once your civilization builds the big lasers, the huge reactors, the advanced materials and the guidance systems, it becomes a very intense but too straightforward engineering project. You still have to solve beam pointing, sail stability, radiation, dust impacts, but you are not fighting bone loss, cancer risk, closed ecosystems, or multi-generation psychology on top of that. So yes, when you ask, how long would it take us to travel 1 light year? The honest short-term answer for humans is still far too long. But for robotic probes, once the infrastructure is there, the answer can drop into the single-digit years, with data coming back decades before any crewed starship is possible. We will almost certainly map and sample our first light year of interstellar space with machines, and only then even think seriously about sending people. And even then, there's another trick we already use inside the solar system that seems like it should help: stealing speed for free from big planets and stars. So the next question is, if we lean as hard as we can on gravity assists and slingshots, can they actually cut down that 1 light year travel time in a meaningful way? Or are they just clever hacks that break down once you leave the neighborhood of the sun? You've seen how shrinking the payload and using robots changes the game, so the next obvious question is, can we also squeeze more speed out of gravity itself? And does that actually help with a 1 light year trip? Gravity assists are one of the smartest tricks we already use. When a probe flies past a planet like Jupiter, it doesn't just fall in and climb back out, it exchanges momentum with the planet. From the probe's point of view, it gets a free speed boost or a re-erect without burning extra fuel. Missions like Voyager 2 used a chain of these flybys to reach trajectories that would have been impossible with onboard propellant alone. With the right approach angle and timing, you can boost a craft's speed by tens of kilometers per second relative to the sun. That's a huge deal for exploring the solar system, but there's a ceiling to how much help gravity can give you, and that ceiling is set by the speeds of the bodies you're stealing from, and how deep into their gravity wells you're willing to dive. Take Jupiter as an example. It orbits the sun at about 13 kilometers per second. That's your basic scale for the speed you can borrow in a flyby. You can add or subtract a chunk of that depending on your trajectory, but you're not magically jumping from 30 kilometers per second to 30,000 just by swinging past it. Push the idea harder and look at the sun. Near the sun's visible surface, the escape velocity, the speed needed to break free from its gravity is about 617 kilometers per second, around 384 miles per second. That's much larger than planetary values, so in theory, if you dive in close and combine a powered burn with the gravitational slingshot, you can leave the solar system with a very high speed in the hundreds of kilometers per second range. That's great for interplanetary and maybe interstellar precursor missions, but it's still nowhere near the 30,000 kilometers per second that correspond to 0.1 C. People have talked about extreme solar dive trajectories where a craft plunges very close to the sun, uses both its engines and the sun's gravity to reach speeds in the thousands of kilometers per second. On paper, if you could survive that environment, you might get out to something like 1,000 kilometers per second. That is about 0.0033 C, 1/3% of light speed. Impressive compared to current probes, but when you run that speed against 1 light year, you're still looking at roughly 300 years of travel time. You've upgraded from thousands of years to a few centuries, but you haven't cracked the problem. The reason we don't do dives that extreme already is obvious: heat and stress. Getting very close to the sun means bathing your craft in intense radiation and particle flux. The solar energy hitting your heat shield scales up violently as you get nearer. The materials we have now can handle certain levels, as with Parker Solar Probe, but there's a limit before everything starts to melt vaporize, or structurally fail. So it's not that the math says no, it's that the materials and thermal protection say back off, long before you get those fantasy speeds. In theory, you could go beyond normal stars and try to use really dense objects, neutron stars or black holes, to steal huge amounts of energy through gravitational assists. They have deep gravity wells and very high orbital speeds for matter around them, but that comes with its own nightmare package. To pull off such a maneuver, you need absurd navigation precision, because the safe window where you get a good assist without being torn apart by tidal forces is very narrow. Get too close and the difference in gravity between the front and back of your ship can literally rip it apart. On top of that, the radiation environments around these objects are extreme. You're trying not to get cooked, not to be shredded by particle jets, while threading a path through a deadly region of space-time. So yes, in principle, you can imagine big gravity boosts from exotic objects, but in practice you're trading go faster for probably die horribly. At some point the margin for error is so small that it doesn't matter that the speed on paper looks great, because no realistic vehicle and guidance system can hit that tiny window reliably. This brings you to the honest conclusion. Gravity assists are fantastic tools for shaping orbits, saving fuel, and squeezing extra delta V out of planetary systems. They are why we can tour multiple planets with one probe. They can give you tens of kilometers per second for free, and that's a big deal for solar system missions. But for light-year scale trips, they are tweaks, not solutions. If your baseline trip time is 4,000 years at probe speeds, gravity assists might cut that to 3,800 or 3,500, or if you pull off something extreme, maybe a few hundred years with an aggressive solar dive, they might shave years or decades off a multi-century journey. What they do not do is turn a 4,000-year slog into a 40-year mission. For that, you still need fundamentally new propulsion energy, higher exhaust velocities, and massive power budgets. Gravity is a helpful hack inside a system. It is not a substitute for the kind of engine you need to make 1 light year feel like a realistic target. And once you accept that, you're forced right up against the biggest wall of all. Even with every trick in the book, there's a hard limit you cannot cross, the speed of light itself. So the next question is, if light is the absolute speed limit, and we can't cheat that, what does that do to the ultimate minimum time for a 1 light year trip, even in the far future? You've pushed gravity, nukes, fusion, and giant lasers as far as they'll go, so the next blunt question is, why not just skip all of that and go full sci-fi, warp drives, jump gates, shortcuts? What actually stops you from just going faster than light and crushing the 1 light year distance in, say, a week? Every piece of tested physics you have says the same thing. The speed of light in a vacuum is a hard limit for anything with mass or any signal-carrying information. As your ship's speed gets closer to that limit, its energy in the frame you care about starts to blow up. In relativity terms, the energy needed for each tiny extra nudge in speed grows without bound as you approach light speed. At low speeds, you add fuel, and your speed goes up in a way that feels reasonable. Near light speed, you add fuel and the speed increase you get back keeps shrinking. To actually hit light speed, you'd need infinite energy. Infinite energy is not a very big number. It's a mathematical way of saying this never happens for real. So any realistic propulsion system you build, chemical, nuclear, fusion beamed, or something more advanced, can only ever take a massive ship to some fraction of the light speed, 0.1 c, 0.5 c, 0.9 c, maybe 0.99 c if you are insanely capable, but never 1.0 c. That is built into the structure of space-time as far as we can measure. What about the cute loopholes you hear about? Wormholes, warp bubbles, bending space instead of going through it? General relativity, the theory that describes gravity as curvature of space-time, does allow some weird mathematical solutions. You can write down shapes of space-time where 2 distant points are connected by a tunnel, a wormhole. You can write down metrics where a bubble of space moves faster than light relative to faraway points, a warp drive. On paper, those things let you get between 2 locations faster than a light ray, moving through normal space would. But those solutions come with a price tag, They require matter and energy arranged in ways we have never seen. Most practical designs need exotic matter, something with negative energy density, or stresses and pressures that violate energy conditions you normally assume are true. We don't know how to make that kind of stuff. We don't even know if it's physically allowed on macroscopic scales. Right now, they are beautiful bits of math that say, if the universe gives you impossible materials, then you can do impossible things. That is not an engineering roadmap, that is a warning label. On top of that, faster-than-light motion in relativity tends to wreck cause and effect. If you let information or objects outrun light, you can juggle reference frames in such a way that an effect can show up before its cause, from someone's point of view. That's what people mean by causality violations. You can set up paradoxes where a message is received before it is sent, or a ship arrives in time to prevent itself from ever leaving. Whenever that happens in a theory, you have two options. Either you accept a universe where logic breaks, or you assume that somehow the universe does not let those trajectories exist in reality. Every precise test of relativity so far, from particle accelerators to GPS satellites, has reinforced the same picture. No massive object has ever been seen to reach light speed, no signal has been seen to outrun it, and all observed physics respects that limit. Whenever someone thought they saw something faster than light, it turned out to be a measurement error, or an illusion caused by geometry, not actual superluminal travel. So if you want to base your light-year timelines on what physics really allows today, you have to take seize the limit seriously. Now connect that hard limit back to the simple distance. 1 light-year is defined as how far light travels in 1 year in vacuum. If nothing can move faster than light locally, and information cannot outrun it, then in the rest frame you care about, you can never beat 1 year per light year as the absolute minimum. You can get close by going at 0.99c or 0.999c, but you can't make the outside observer's clock say 6 months for a full light year of real distance. There is always some number greater than or equal to 1 year attached to each light year, as long as you ask the question from that frame. That's the key point for travel times. No matter how advanced your tech becomes, as long as it obeys the physics we know, you will never get an answer like 1 week for 1 light year. As seen from home, best case in some far future, an insanely advanced ship might do something like 0.99c and make the outside observed time only slightly more than 1 year per light year. You can squeeze the factor above 1, but you can't push it below 1 without throwing the entire structure of relativity in the trash. So what can you actually do inside those rules? First, you can push your cruise speed close to light speed. You can build better engines, better fuels, and bigger power infrastructure so that 0.1c, 0.2c, maybe 0.5c or more become reachable for certain classes of missions. That lets you reduce the time it takes in the outside frame down toward that 1 year per light year floor. You can never cross the floor, but you can move down toward it from the thousands of years ceiling where we are today. Second, you can exploit time dilation on the ship. The closer your velocity gets to light speed, the more your onboard clock slows relative to the outside frame. So while Earth's clocks say the trip took, say, 12 years to go, 12 light years, the crew on the ship might only experience 6 or 7 years. For them, subjective travel time shrinks as they approach light speed. You are trading energy for your own experienced years. Third, you can optimize your trajectory. You can design propulsion systems and mission profiles that get you up to cruise speed quickly, using high thrust at the start and end instead of crawling gradually. You can shave off mission time by reducing how long you spend in low-speed phases. You can also bend your path slightly with gravity wells to get small boosts or to save fuel, but as you've seen, those are minor tweaks at the interstellar scale. When you put all of this together, you get a clear bounded answer. For any given frame of reference, the minimum possible time to cross 1 light year is never less than 1 year, because light itself sets that baseline. Real ships that obey physics will always take a bit longer than that when measured from that frame. You can use insane amounts of energy to get close. You can use relativity to make the trip feel shorter to the people on board, but you can't cheat the outside clock. So now, when you ask, how long would it take us to travel 1 light year, you can see 3 layers. With today's tech, it's thousands of years. With advanced nuclear and fusion systems, it might shrink to decades. With near light speed drives in some distant future, the outside answer never drops below a little more than 1 year, while the onboard answer can drop into a few years, subjectively. You can bend the numbers, but you can't break them. And that brings up one last important piece. If we can't cheat light and we know the lower bound on time, we'd better be very sure we know how far a light year really is, and how we measure those distances in the first place, because any error there directly contaminates the timelines we're fighting so hard to achieve. Right now you've got this huge number in your head, 9.46 trillion kilometers for a light year. So the next obvious question is, how sure are we that this number is real, that these distances aren't just big guesses? For the nearest stars, the method is very direct. You use parallax. As Earth moves around the Sun once a year, your viewpoint shifts by about 1 astronomical unit, roughly 150 million kilometers. Against that motion, nearby stars appear to wiggle a tiny bit compared to the distant background stars. You measure that tiny angle, you know the size of the baseline, 1 astronomical unit, and you solve a simple triangle. That gives you the distance in kilometers or meters. From there, converting to light years is just how far does light go in 1 year at 300,000 kilometers per second, which is where the 9.46 trillion kilometer figure comes from. So for nearby stars, 1 light year away is not a guess, it's geometry. Telescope sees an angle, you know your orbit size, done. That's the first rung of the distance ladder. But parallax only works cleanly out to a certain range. As stars get farther away, that apparent wiggle shrinks. Eventually, even with very precise instruments, the angle becomes too small to measure accurately. So for more distant objects, you switch to other tools, things called standard candles. A standard candle is an object whose true brightness you have good reason to believe you know. Certain types of variable stars, like Cepheids, have a tight relationship between their pulse period and their intrinsic luminosity. Certain supernovae, like Type 1a supernovae, also have reasonably standard peak brightness. You observe how bright they look from here. If you know how bright they really are, and how dim they appear, you can work out how far away they must be, because light spreads out as it travels. You then combine these brightness-based distances with other measurements like redshift, which tells you how much the light's wavelength has been stretched by the expansion of the universe. Step by step, you build a cosmic distance ladder. Parallax calibrates the nearby standard candles. Those calibrate brighter standard candles further out, and so on. Each rung is cross-checked against others, using different methods and different types of objects, so no single technique carries the whole load. Back to parallax for a second, because it's more powerful now than it has ever been. Modern space missions, like precision astrometry satellites, can measure parallax angles down to microarc seconds. That is an insanely small angle. In visual terms, it's like detecting the apparent shift of a coin seen from thousands of kilometers away. With that level of precision, distances to nearby stars are known to within a few percent or even better. The 9.46 trillion kilometers per light year number does not come from guessing distances. It comes from 2 things we measure extremely well: the speed of light and time. We know how fast light travels in vacuum per second. We know how many seconds are in a year. Multiply those, you get the length of a light year in meters or kilometers. The uncertainty there is tiny. The main uncertainties come from measuring how many of those light years away a given star actually is, and for nearby stars, those uncertainties are also very small now. Why does that matter for travel? Because all of your brutal energy and propulsion math scales directly with distance. If you think a target is 1 light year away, and it's actually 0.8 light years, you overbuild your fuel and energy budget. If it's 1.2 light years, you underbuild and your ship never gets there. When you're talking about pumping 10 to the 20 or 10 to the 21 joules into a mission, you can't afford to be casual about the distance. A 20% error in distance is a 20% error in the energy you need, the fuel you carry, and the time you plan. Having a solid cross-check distance scale means that when you say Proxima Centauri is about 4.24 light years away, you can plug that into your trajectory design with confidence. You know how long it will take at 0.1 C, 0.2 C, 0.01 C. You can size your engines, your radiators, your shielding, and your life support based on solid numbers instead of hand-waving. The map is not approximate anymore. It's precise enough that the main uncertainty is not how far, it's can we actually build the thing to get there? That's the real point here. The universe has given you an extremely accurate map. Distances to nearby stars in light years are known to many decimal places, using multiple, cross-confirmed methods. The light year itself is tied back to the speed of light in atomic time standards. On the measurement side, the floor is rock solid. What's not solid is your engineering. The limiting factor is not whether a light year is really 9.46 trillion kilometers or 9.45 or 9.47. The limiting factor is your ability to design machines that can survive high speeds, cosmic rays, dust impacts, waste heat, and decades of operation, and your ability to organize a civilization that's willing to spend planet-level energy on one mission. So by the time you ask how long would it take us to travel 1 light year, you're not doubting the distance. You're staring at a well-measured gap and asking, given this fixed gulf and the engines, energy, and biology we have, what timescale do we actually end up with? And that sets you up for the last step, pulling all of these pieces together into one honest summary, from jets to probes to nuclear drives to beamed sails, and seeing in one place what 1 light year really costs in time for each technology level your civilization might reach. So after all of this, the real question you care about is simple. When you put every number on one line, how long does 1 light year actually take for us, right now, and for us in different futures? Start with the raw scoreboard, no fluff. At the slow end, a commercial jet, cruising at about 900 kilometers per hour, around 560 miles per hour, would need roughly 1 million years to cross a single light year. That is where normal human experience sits, totally disconnected from interstellar distance. Move up to the fastest hardware we've actually flown, deep space probes that hit about 70 kilometers per second, around 157,000 miles per hour, still need over 4,000 years to cover 1 light year. That is already beyond recorded human history. Give yourself an aggressive nuclear thermal system, something that can push a craft to around 200 kilometers per second, roughly 447,000 miles per hour. That cuts the time for 1 light year down to about 475 years. Big improvement, but still multiple human lifetimes, still closer to founding a dynasty than running a mission. Step into serious nuclear pulse territory, where your ship reaches around 1% of light speed, 0.01 C, about 3,000 kilometers per second. Now, 1 light year takes on the order of 100 years from the point of view of someone watching from your starting point. You have officially moved from millennia to century. Jump to optimistic fusion performance with cruise speeds around 10% of light speed, 0.1 C, so about 30,000 kilometers per second, 18,600 miles per second. 1 light year sits at roughly 10 years of outside time. That is your first clean decade-scale answer that uses only real physics. Push even harder or even harder to tiny beamed sail probes at 0.2 to 0.3 C, 60,000 to 90,000 kilometers per second. Now 1 light year drops to around 5 years at 0.2 C and a bit over 3 years at 0.3 C. Those numbers are all measured by an external observer. At the high end, because of time dilation, the people on board, if there were any, would experience less time than that, but you never beat the 1 year per light year limit as seen from outside. So what's the realistic answer if you stick to tech that doesn't rewrite physics and doesn't demand godlike infrastructure? In the next century or so, with serious investment but without breaking known laws, the plausible tools are nuclear thermal rockets, very advanced electric propulsion, maybe early, constrained nuclear pulse systems. With those, for large, significant payloads, 1 light year is still in the range of hundreds of years to a few thousand years. You're not doing 10 years with a crew, you're doing multi-century robotic arc if you fly something big. But if you focus on tiny robotic probes instead of crude ships, and you're willing to build massive power and beaming infrastructure in the home system, the picture sharpens. A gigawatt to terawatt class laser array pushing gram to kilogram scale sails could, in principle, get travel times for 1 light year down to a few decades initially, and then, with mature systems, into single-digit years. That is still a giant engineering project, but it is in the realm of global effort, not magic. Farther out on the timeline, in a mature high-energy civilization, the numbers look very different again. If you master practical fusion propulsion, can run reactors that accelerate exhaust to huge speeds, and can sustain global-scale power for long periods, crude ships cruising at around 0.1 C become thinkable. In that regime, a 1 light-year trip costs on the order of 10 to 15 years in the rest frame. Because of relativity, the crew on board might experience a bit less than that, but for people back home, the clock still says roughly a decade plus acceleration time. That kind of future doesn't let you teleport, but it does go to a star 1 light-year away into something more like a very serious career mission, instead of something your great-grandchildren might see end. Underneath all of that sits the hard flaw. As long as known physics stands, the absolute minimum time to traverse 1 light year, measured in the frame of your departure and arrival, is 1 year, because that is how long light itself takes. You can get arbitrarily close to that bound with ridiculous amounts of energy and perfect engineering, but you can never run a massive ship at exactly light speed. So the real hard limit answer is, no matter how advanced you get, you will always pay a bit more than 1 year per light year in the outside frame. So when you ask, how long would it take us to travel 1 light year, you're not asking for a single static number, you're really asking, how far are we as a civilization willing and able to push energy, engineering and human biology? Right now, with chemical rockets and a handful of fast probes, the honest answer is thousands of years. In a bold nuclear future where fission and early fusion drives are routine, and we use huge reactors in space, the answer drops into hundreds to tens of years, depending on whether you send humans or robots. In a mature fusion and beamed power civilization, one that treats multi-terawatt laser arrays and fusion drives as normal infrastructure, a light year can fall to a few years as seen from outside, and maybe even less as felt on board, thanks to time dilation. The distance itself never moves. 1 light year is always 9.46 trillion kilometers, about 5.88 trillion miles. What moves is your capability. The timeline you get back is basically a mirror. It reflects how advanced you are, how much energy you can control, how much mass you can push, and how long you can keep fragile systems, including human bodies and minds, alive and stable in the dark. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.